So that's our 1s. What does the s orbital look like? It's a sphere, circle drawn-ish. Right? The electrons that can fit into that one type of orbital. There's only 2 electrons that can go in. So if we just have that one type of orbital, how many total electrons can make it into that energy level?
2.
Just 2. Okay? And if it, oh, there you go, some big bold letters. What happens if we move up to the second energy level? Okay, up to the second energy level, we now get 2 different types of sublevels. We're at the second energy level, so we need to specify that. We'll have an S, and we will also have a P type show up. The S, being a sphere, only has one possible orientation. The P, being the dumbbell shape, ends up with 3 official orientations. This one's the sketchy one coming in and out of the board at us. Okay. Each of those orbitals can fit 2 electrons. So the s orbital fits 2 electrons. How many electrons total in my p sublevel? 6, because each of those p orbitals can hold 2 electrons. So total in the second energy level, I have 8 electrons. Okay, kind of makes sense? What happens if we jump up to the third energy level? We will have both the types of orbitals that we had before and a new one. Right, so we'll have S, P, and D. These will be 3S, 3P, and 3D, so we're specifying their level of energy. Our S is that sphere, our P is the dumbbell, and then our D is a horribly drawn clover leaf. Okay. With our s orbital, again, there's only one orientation, so we can only fit in 2 electrons. With our p orbital, we have 3 orientations, so we can fit in a total of 6 electrons. With our d orbital, we have 5 orientations, which means we can fit 10 electrons. Which means in our second energy level, we have a total of
8.
Third? Oh, third energy level, we have a total of 18 electrons. Okay, kind of makes sense? Okay. Try to not get too bogged down in the details of the shapes and all that fun stuff. Pick up kind of some of the memorization of what's happening within these. Okay. Theoretically, if you move through chemistry, in 3 years of chemistry, you might actually learn why you have these shapes. Okay. But that's 3 years of chemistry to get to that point. Okay, so at this point, you just need to acknowledge that they exist, and that's kind of how we can manipulate and work with them. Okay.
For the purposes of class, we're only going to D?
We will cap out at D, absolutely, for this class. Arguably, we cap out at P. Okay? So you're responsible for understanding what the d orbital looks like, but you aren't going to be doing too much as far as putting electrons into that space. You'll see it pop up a little bit because those d orbitals hit with our transition elements. Okay? But very rarely do you see questions about those transition elements. It'll pop up, I'm sure, in mastering because you need that practice. But primarily, you're looking at the S and the Ps. Okay? That, I think, steps-wise out all of that. And we could even drop in our fourth energy level where we bring in the F orbital. Okay, all that fun stuff. So when we're looking at putting electrons into these orbitals, so now what we want to do is, now we have these orbitals, how can we build our atoms? Where do the electrons exist? So if we move to hydrogen, how many electrons does hydrogen have? 1. Where should I put that 1 electron when it comes to hydrogen? Why the first energy level? There's spots all the way through that. I can put that electron any place I want. Why do I put it in the first energy level? It has to do with it being close to the nucleus. Why being close to the nucleus?
It's a smaller density.
Not quite. Lower energy. It's closest to the positive charge. We're neutralizing the charge as best we can. The lower energy state is our more favorable state. So we always put our electrons in, starting lowest energy first, and slowly work our way up. So if we were going to look at hydrogen, we could go through and with this diagram, we can say, oh, there's an electron sitting with hydrogen. Remember we said vaguely that term of spin state, not that big for you to know, but in this case I'm saying the spin state is aimed up, real fancy. If I move to helium, helium has how many electrons? 2 electrons. Where do I put that second electron? Why the first energy level? Lowest energy, but it's not just lowest energy anymore because there's an electron there, right? Okay, what happens when we get an electron near an electron? They repel. So remember our electrons had this spin state. They can spin opposite directions. Each orbital can hold 2 electrons. So when I move to helium, yeah, I can put it there. I can put my second electron in, and we typically show it with the arrow pointing, of course, the opposite direction of the other one to represent the opposite spin states. Right? Move to lithium. Where's the electron go for lithium? Or sorry, how many electrons does lithium have? 3. Where's the electron go for lithium? Okay, so we put in our 2 first at our first energy level, and where's that third electron go? Okay, but what happens to our second energy level? Splits into 2 states. Of those 2 states, where does the electron go for lithium? Always go to the lower energy level, which is going to be the 2s. So when we move to lithium, there's our extra electron. Let's keep it in red. What happens when we move to beryllium? How many electrons does beryllium have? 4. Where do the first 2 electrons go?
1s.
The 1s, so it's already drawn. Nice. Where's the next electron go?
2s.
2s. Where's the next electron go?
2s.
Also to the 2s. It's still lower in energy. Boron? Where should I put? It is boron, heck yeah. Boron has how many electrons? How do you know it has 5 electrons? Okay. On our periodic table, it has an atomic number of 5, and we're assuming neutral, because I'm not saying it's charged. So it's got to have 5 electrons to balance out those 5 protons. Where do the first 2 electrons go? 1s. Where's the next 2 electrons go? Next electron.
2p.
Into the 2p. Okay, so here's maybe what your hand's going to ask. What are you going to ask?
I was just, so they just split by 2s and you just go up.
Up to this point. So now let's push the next question. Maybe this will get what you're asking about. Carbon. How many electrons does carbon have? 6. Okay, so now we run into an interesting dilemma. Where does that 6th electron go? Why the next 2p orbital and not the same one that we already have an electron?
Fill those 3 and then do the second round, right?
Why do we fill those 3 first?
Because I don't know, I just guessed. I'm not gonna lie.
What happens when you get an electron near an electron? They repel. The only time that we actually move up to a higher energy level, okay, is if there isn't a hole already available. If we go through and take a look at our 2p orbitals, all 3 of those orbitals are all the same energy. Okay? The only reason I want to double is if there's not another place to put the electron. Well, with the 2p orbitals, is there another place to put the electron? Yeah, I've got one of the other 2p orbitals. So we will half fill before we double. So when we move to nitrogen, where's the next electron going? Our third p orbital. We move to oxygen.
3.
Fill in the first p.
We'll now go back and double our p orbitals before we jump up to the third energy level. How do we know that that's the case? Where is oxygen on our periodic table?
8.
Which row?
3rd.
Which row? Try again.
2nd.
Second. Okay. If we jump to our third energy level and started putting oxygen's electrons into the 3s, where should oxygen show up on the periodic table? In the 3rd row. It shows up in the 2nd row for a reason. We're still filling the 2nd energy level. Okay? But we're now double filling are p orbitals. Yes?
So if you're writing it out, it's CV1s, 2s,
That's the next question.
2p 3 times, or just 2p?
So if we're asking now for an electron configuration, okay, one way to go through and do it is to draw out this diagram and start putting in the electrons into each of those orbitals and labeling them all up. Okay? So to answer a question about the electron configuration of any element, you now have a page filled with all this information. Is there a way we could condense it? Okay. That condensing now goes through and says, okay, for oxygen, where do I have electrons? Well, the first two electrons went where? Into the 1s orbital. So I've got the 1s orbital. How do I signify there's two electrons there?
To the second.
Use my superscript. I've got two electrons in that orbital. Okay. Let's make sure I've got oxygen actually drawn here. Okay. Where's the next set of electrons go?
2s.
Into the 2s orbital. How many electrons are found in that orbital? What's my next energy level?
2p.
The 2p. How many electrons are found in my 2p orbitals? 4. Okay. Is it possible to subdivide your p orbitals out? Yes. You are not typically asked to do that. So if you're asked for the electron configuration, really what we're asking for is what we just wrote out for our oxygen. Right there. Is it equally valid to go through and say the electron configuration for oxygen is 1s2, 2s2, 2p2, 2p1, 2p1? Yeah, it's just kind of a bit redundant. Okay? But it does give us a little bit more information because now we're saying we've got those electrons in those 3p or those 3 2p orbitals. Make sense?
So like that last element, UUO-118, is that why? Because it's in the 7th row, it's on the 7th level. Is that why it's like falling apart basically because it's so close to the vacuum?
Exactly right. So when we look at UUO, what's happening is we're now putting electrons so high in energy that they are now effectively in the vacuum. Well, in the vacuum means they're not attached to the atom anymore. So we do tend to run into a theoretical limit for our periodic table because we now we physically can't put anything more around it before it just falls apart on its own. Okay? And that's why those aren't stable. Okay? And why they're also unnamed now, because we had to make them. Because they are that unstable. Okay? Other questions? Okay, so as we go through this, our periodic table actually gives us the information. So hydrogen, 1s, helium, 1s2. Lithium, we'll have our 1s2 and 2s1. Why no 2p's?
Because not after the right side, right?
Okay. Our p's were over on the other side of the periodic table. We aren't there yet. Okay. What happens when we move down to sodium? We'd have 1s2, 2s2. Let's clear all this away. Sodium, 1s2, 2s2. What's the next thing we fill? 2p6. We're moving through the column, and then 3s1. Right? What if we jump to argon? So 1s2, 2s2, 2p6, 3s, 2, 3p, 3p6. We now have argon. Any guesses what the next question is going to be? Potassium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1.
doesn't it fill with a D though?
Why did it not go to the D? Very valid question. Okay. There's some symmetry options that happen out of this as to why it doesn't go into the D. You'll notice that I can't really subdivide any further. Each of those orbitals is getting closer and closer in energy. So if I break down that yellow, we've got our S, we've got our 3 Ps, and we've got our 4, did I do the 5 Ds? 4 Ds. What's the difference in energy between my 4s orbital and my 3d orbital? They are almost identical in energy. So that new electron that's coming in, where should it decide to fill? Okay, and this is where it gets a little bit weird. Do we put the electron in one of 5 possible options or in one of 1 possible option? Okay. Well, the answer clearly is 1 of 1. Why? Okay, it kind of comes back to a symmetry argument. Our molecules are trying to achieve symmetry. And typically most people say, well, symmetry, that's a load of crap. Why do we have to evaluate that? Think of the most beautiful person you know or handsome person you know. Okay? You can close your eyes. Don't look at me. I don't want you thinking of me. It's not going to be a fair comparison. Okay? Think about the symmetry of that person. Look at their face, their body. Symmetry, is it there? It is. Okay? We strive for symmetry. Symmetry is something that is kind of ingrained into ourselves. You think about the ugliest person that you can affiliate with. Why are they classified as ugly in your brain? Think back to the symmetry. They're not very symmetric. Oh, thank you. I appreciate that. Looking right at me? Is that what I heard? Oh, okay. Well, that's fair enough. You can do that then. Right? So it comes back to a symmetry argument. If I'm half filled in one place, that is more symmetrical than being half filled with 5 possible states. Okay, so we can use this kind of hand-wavy argument of symmetry being a better option. So that when we then move to calcium, where do we put the next electron for calcium?
In that same orbital.
We put it into the same orbital, and it becomes 4s2. Okay, again, to maintain the symmetry. But where's the next electron go? When we move to scandium.
Into the 3D.
Now it drops into the 3D. Why? The difference in energy between the 3D and the 4p is now great enough that it goes based on energy, not symmetry. Okay? A little bit of a weird concept. Okay, so we're just kind of touching base on it so you're aware of that. Okay? You'll hear more about it in 151. What's the reason why we don't have to go into it a lot of detail? Your periodic table tells you that information. These first 2 columns are often referred to as the S block. Why? If you look at their electron configuration, the highest energy orbital with those 2 columns is what orbital? S orbital. From scandium all the way over to zinc, those elements are typically referred to as the, don't tell me transition elements, you're right, but don't tell me transition elements. The D block. Why? When we look at their electron configurations, their highest orbital level is the D orbitals. From boron over to helium, neon. That section is typically known as the P block, because when we look at our highest energy orbitals, they are the P orbitals. The last 2 rows, S, P, D, F. There's our F orbitals. Okay? So your periodic table gives you that filling information just by moving through it kind of linearly. We do run into a kind of offset issue because scandium fills what? It fills the 3D, even though it's in the 4th row. Okay, so your transition elements are offset by 1. Okay, as far as your energy levels go. Okay, but everything else kind of follows sort of pseudo-naturally. So I saw some hands.
So when you fill 4s2, and then you go back to 3d1,
Mm-hmm.
do you just, like when you write it out, you just leave it as 3d1 and then 4s2? Like, and you just keep it like that, right?
Scandium, 4s2, 3d1. Most commonly, it's written like that.
Okay.
Depending on notational things, sometimes you'll see those interchanged, but it's typically written in this order.
Okay.
There was a hand in the back, yes.
What about for boron with the symmetrical thing happening with the 2p?
So the difference in energy between the 2p and the 3s is big enough that it fills the p orbitals instead of the s. Yep. Which is, again, why we see the pattern that we've got out of it.
I'm sorry, did you say that the 3D would go before the 4S? Or is it?
It's typically written 4s then 3d. Okay. And again, it sometimes depends on someone's meaningless notational change. So you might watch out for that when it comes to sapling. But it should be written in this format, because that's how it fills. Do you still have a question?
So even though it's still not technically symmetrical, because you still have those 4 left in the D.
True, but we're forced unsymmetrical. We don't have a choice. So in the case of our potassium, we had a choice to be more symmetrical versus completely unsymmetrical. In this case, we don't have a choice. We have to be unsymmetrical. Okay? So let's kind of spitball an idea here for scandium. What do you think its common charge is? If we make scandium an ion, okay, what do you think it's going to want to do? So when we go to charges, what do we change? Electrons. What do you think scandium's going to do?
Fill in the 3Ds.
Fill in the 3Ds, so it's going to accept 9 electrons?
No, I'm just kidding on that.
Well, that's a possibility. It could accept 9 electrons, and then that d orbital is nice and symmetric. What's the other thing it could do? It could take away the 1 electron, and now it's symmetric. So which charge probably makes more sense? Taking it away, and our scandium probably carries what charge? A positive as opposed to the negative. Okay? Kind of, sort of? All right. So you'll see this table show up. It's a filling diagram for how you go through and fill these, running through the exact same process that we just went through and did, except I gave you kind of a reason why we filled the 4s before we filled the 3d. This figure just shows that that's what's happening, but it doesn't really explain why. Okay? Because you'll notice that the 3d is still shown at a lower energy than the 4s. Okay? So it doesn't make sense to our standard patterning. But that's the fill pattern. So if for some reason you happen to forget and you don't realize that you can look at the periodic table to tell you your electron configurations, you can have memorized this little figure and draw that little zigzag path through it, which I always screw up. So if you can get that right, good job. Okay? You were probably going to get it right anyway then. Okay? Questions? Okay. We also have an interesting concept popping up here. This idea of the valence electrons, which is going to become important when we talk about bonding, which is chapter 12. So if I take a look at a relatively small element, let's look at carbon. Its electron configuration is 1s2, 2s2, 2p2. Okay, so we got the 6 electrons for our carbon. Valence electrons is referring to our highest energy electrons. Why might we look at the highest energy electrons? Where are our highest energy electrons relative to the nucleus? They're furthest away. Why might that be important? Particularly when it comes to bonding. What's going to be the first thing that interacts when you take 2 atoms and you bring them near each other? The electrons, and it's going to be the highest energy electrons because they're the furthest away. So when we're talking about bonding, we are very often going to make reference to valence electrons because those are the electrons that are most likely involved in bonding. So what are our highest energy electrons for carbon? 2p is absolutely a high energy sequence of electrons.
Those
2s is also included in it. Okay? So when we're looking at our valence electrons, what we're looking at is the energy level. Okay? So for carbon, our energy level is 2, is our highest energy level. Anything in that second energy level counts as a valence electron. Okay? If we move to silicon, what would our valence electrons be? I'll let you guys think about that one, write that out. So you can give me the electron configuration for silicon. And tell me what your highest energy electrons are. Your valence electrons. Some of you seem to be sharing with each other, so you can share with people. You don't have to just think this to yourself. I didn't say that's silicon's electron configuration yet. How many electrons have we specified so far? 10. How many electrons does silicon need? 14. So this is not the complete configuration. We have to move to the next energy level. What's our next energy level? 3s2, 3p2. What are our valence electrons? The 3s2 and our 3p2. So a question that could be asked is, first off, what orbitals are involved in our valence electrons? We can say 3s and 3p. I could also ask, how many valence electrons does silicon have? It has 4. Right, so we just add them up. That how many valence electrons does an atom have is a really, really common question. It might be nice if we had a shortcut for that. Where's hydrogen? Column number 1. Beryllium. 2. Boron. Carbon. 4. Where's silicon? In the 4th column. How many valence electrons did it have? 4. There it is. Hallelujah. Number of carbon, or the number of columns across, gives you how many valence electrons are in your atom. A real quick shortcut. You don't have to calculate anything. That kind of works out nicely.
Does that work for the transitional elements?
Does sort of works for your transition elements. Yeah, it's a little bit different. I wouldn't stress about those. It is kind of going to work. You just have to fold in the p orbitals as well. Did anybody actually write out the electron configuration like I did? Okay, thank you for those of you that raised your hand and actually did what I asked you to do. I appreciate that. Okay, which is now going to be the next question. I wish there was a shortcut to writing that out. Is there a shortcut?
Yes.
What element has the electron configuration 1s2, 2s2, 2p6? Neon. So the electron configuration for silicon is neon plus 3s2, 3p2. Okay? A little bit shorter. That's not too bad. That actually works out okay. Okay? Up to you which one you want to deal with. With the shortcut method, by definition, the only elements that we will use as our shortcut term have to be noble gases. Okay, those are the only ones we're allowed to use as shortcuts. Okay, so I won't say the electron configuration for silicon is aluminum plus a 3p orbital. Okay, that doesn't count. Yeah, 3p1. That doesn't work. Okay, so that doesn't work. We have to use the noble gases, that last column. Okay, that last column. So I saw 1, 2. Was that a hand? Mm-hmm. Go ahead.
Okay, I might be totally off, but.
That's fine.
So, it'll only change, like, how many it can carry, like, the P6,
Mm-hmm.
the very first time you see the new, figure thingy? Because, like, otherwise it goes 3p2, back to 2 for the P, you know?
Because you're moving to a different energy level. So the P6 happens because I have now fully moved all the way across that second energy level, and I now have to drop down to the third energy level. For me to drop down to that third energy level, the previous energy level needs to be full.
So if you kept going, it would still only, the 3p would still only carry 2 though, right? Even if you went to, like...
So if I move to the next atom, phosphorus, what would the electron configuration be for phosphorus?
3p3. Well, that's all you changed.
So you can still
So when I move to
Yeah, you want to
phosphorus,
fill the gap.
all p orbitals, or the total p orbitals, can hold 6.
Okay.
So we could go through and say, oh, that was a horrible color to pick. Is that better? Shows a little better. Right. We could go through and say it's 3p2, 3p2, 3p2 for each of those, but we can condense that into saying just totaling how many electrons in all of the p orbitals.
So all the P's can carry 6 and all the D's can carry...
The entire p orbitals, all 3 of them in total, can carry 6.
Okay.
Yes. A single p orbital can hold 2 electrons. A single d orbital can hold
2.
2 electrons. How many electrons fit in all d orbitals? 10. Very subtle change in the question. Okay, make sure you read the question very, very carefully. If we're referring to a single orbital, it's 2 electrons, period. If we're referring to the type of orbitals, that changes the question. Okay, that depends on what type you're looking at. Was there a hand over here, or was it? Okay, go ahead, Don.
Why only noble gases?
We'll get into why when we look at charges. Okay. It largely comes down to those energy levels are full. That's pretty much it. Other questions? Okay. So we already just talked about this just a little bit. Chapter 5, back to Chapter 5 now, some patterns that come out of your periodic table. Those first 2 columns, commonly referred to as the S block, because their valence electrons hit s orbitals. Right? The next section, typically referred to as the D block, because valence electrons have d orbitals. Right? So we've got those kind of patterns that can kind of fall out of your periodic table. It is organized kind of nicely in that respect. Okay? Questions? You sure? Okay. We'll do a quick quiz. Say it again. Okay, so here we go. Our atomic radius. Down a column, electrons into higher energy orbitals. Higher energy orbitals means bigger, period. Okay? As we go across a row, we're adding more electrons. So we would expect them to get bigger. But it's a question of where are we putting those electrons. As we move from lithium to beryllium, where are we putting that last electron? Or that next electron? In the 2s orbital. So we're putting it in the exact same orbital, which means it has the exact same different distance from the nucleus. Okay. What's that? I don't quite know what that means. What's offset? Then I don't know what I was talking about when I said offset by 1. I'll watch the lecture again and try and figure out what I said. So what's happening when we move up from left to right is we've now added that extra electron, and we put that extra electron into the exact same energy level. Exact same energy level means, at best, no change in size. But what else changes? I get another proton. So I'm now putting a stronger positive charge. Okay, I'm increasing the strength of the magnet. So we can take 2 magnets and get them so they sort of attract each other and just kind of hold them there. What happens if we now double the strength of one of those magnets? They're going to get pulled even tighter and closer to each other. That's what's happening as we move from left to right across the period. Okay? We're putting them at the exact same distance, but we're increasing the strength of one of our magnets. The nucleus is getting stronger. Okay? Kind of a neat process. Really all you need to know is that it gets smaller as you go left to right in the period. Okay? Those of you, anybody moving into organic chemistry? Like 3 or 4 of you? Okay, for the 3 or 4 of you, left to right on a period, when you hit organic chemistry, doesn't change. Same size. Okay? We make a lot of approximations in organic. It's awesome. Okay, so if you aren't taking organic chemistry, you should. Ionization energy. Okay? What ionization energy is the energy required to remove an electron while the atom is in the gaseous state. So we take an atom, we get it up into the gaseous state, and we say, I need to rip that electron away. How much energy does it take? Okay? Number one, should it take energy? Okay? Let's think back to our electron configurations. Okay? If I look at hydrogen with an electron down here, and I look at the vacuum up here, how do you spell vacuum? Oh, that's close enough. To ionize hydrogen, what do I have to do? I have to take this electron, and I have to get it up to the energy level of the vacuum. That's a big energy difference. To do that, I have to put energy into the electron to get it to jump to that state. Okay? So the ionization energy is going to be an input of energy to cause it to eject that electron. So what might happen to the ionization energy as we move through our periodic table? So let's say down a column. If we move to lithium, where's our highest energy electron for lithium? The 2s, right? Should its ionization energy be greater or smaller than hydrogen? What are we trying to break to? To vacuum. What happened to the distance between them? They got closer, which means the energy is smaller. It's a smaller gap. Okay, so our ionization energy is just referencing that. So what we're looking at is that electron. Is it close to the vacuum? If we jump to, say, our 118 UUO, we're now putting an electron right up here. Is that going to have a really big ionization energy or a really small one? Really, really small. Its electron is effectively already in the vacuum state. Okay? All we have to do is flick it and it jumps out. Okay? So that's what's happening with our ionization. And so you then get responsible for looking at trends. Okay? In general, your ionization energy increases as you go from the bottom to the top. Why? Bottom being francium. Where's our electron? In the valence electron is in the s orbital. What was the number? 7th energy level. What happens when we go up to hydrogen? It's in the 1st energy level. So as we go up the column, our ionization energy should increase because it's going to require more energy to rip that guy out of there. Okay? In general, it increases as you go from left to right across the period. Okay? Why? What happened to the radius? From left to right, what did you do to the radius? It got smaller. Those electrons are now closer to the nucleus, effectively lower in energy, which means to rip them out, it's going to require more energy. Okay? So these trends all kind of balance off of each other. Okay? We do run into this issue of in general. Okay? Why do we say in general? Unfortunately, there are exceptions, and those exceptions come from looking at the electron configurations. Okay? So let's see. We got a nice figure here. You notice that we'll have hydrogen at a relatively high ionization energy in comparison to lithium, sodium, potassium, rubidium, cesium, which are all underneath it. Helium has a higher ionization energy than hydrogen. Okay, why? Because it has a larger nucleus, a stronger nucleus. So it's going to require more energy. So that trend makes sense. Hydrogen to helium was perfect. Okay? Helium to lithium, what happens? We've dropped in our column and technically shifted the opposite direction, which means we would expect a significant drop in the ionization energy for lithium. Then what happens? We go up to, what's the element after lithium? Beryllium. And our ionization increases. Well, that makes sense. What happens when we move to the next element? We moved to boron, and what happened? It decreased. Why did it decrease? Well, what's the difference in electron configuration? If we take a look at boron, its electron configuration is 1s2. Sorry, what was its configuration? 1s2, 2s2, 2p1. Why would it be really easy to rip that electron away from the boron?
It's only one.
It's only one unpaired electron, and if we remove it, does that look symmetrical?
Yeah.
Yeah. There's a symmetry argument again. Right? The ionization energy is going to drop because we can improve symmetry by removing that electron. So that ionization energy is going to drop a little bit because it's really easy to kick it out of there because then I look beautiful. Yay, I always want to look beautiful. Right? As we move through this, you'll keep seeing that you get these weird drops every so often. Right? What you should go through and do on your own time, I know you love studying chemistry on your own time, look at the elements that are changing there and look at their electron configurations. Okay? That drop is due to a symmetry effect. Yes?
How can it be the same element if the electron is not there?
What defines the element? The protons, not the electrons. So what we're talking about when we look at ionization energy is we're still maintaining the same element, but now we're changing the number of electrons, which means we're no longer looking at an element, we're looking at an ion, okay, a charged species.
Okay.
Okay? Electron affinity, not talked about in your textbook, but I want to address it real quickly. Okay? This is the energy released to grab an electron from the vacuum. So we look at an atom in its elemental state and we say, grab an electron from the vacuum. How much energy is released? Should energy be released? We're looking at an electron in the vacuum, very high state, versus bringing an electron into an orbital, which is lower energy state. Okay? So we should expect to release that energy in some way. So we could quantify all of that determination. Okay? And you could look at the trends. We don't care about the trends, it's not in the textbook. But the reason why I want to address it is that the balance of the electron affinity and the ionization energy leads us to another massively important concept. Electronegativity. Okay? This is really, really important, particularly for anybody moving into organic chemistry. Okay? Probably 90% of what you learn in organic chemistry comes down to electronegativity. Okay? It is that stupidly important. Okay? What is electronegativity? Okay? Well, electronegativity is the ability of an atom to take bonding electrons from another atom. Okay? So the bigger the electronegativity number, the more likely it's going to take electrons from another atom. So fluorine is our most electronegative and cesium is our least. You'll notice the noble gases don't fall on our table. Why not? Okay. Our noble gases, as we defined earlier, are inert. They don't react. Okay. So they aren't easy to react, so we don't actually even tabulate ionization energies or electron affinities or electronegativities. Okay. The difference in electronegativity is ultimately going to tell us what type of bond we have. So when we talk about bonding, we have to have some understanding of our electronegativity so that we can predict what type of bond. Remember we talked about nomenclature really, really briefly? There were two types of bonds, right? What were those two types? Covalent and ionic. Okay? What was an ionic bond? A metal and a nonmetal. So pick a metal. Let's say cesium. Pick a nonmetal. Let's say fluorine. What's the difference in electronegativity? Really big, really small. It's the biggest difference we can get. Okay? That type of bond means that fluorine is literally reaching into cesium and taking all of the electrons away. Well, if fluorine takes the electrons away from cesium, fluorine has gained electrons. What charge does it become? Negative, because electrons are negatively charged. What charge does cesium become? positive because it lost an electron. What do we call a species that's positive? A optimist? I can see that. Cation. And a species that's negative? Anion. Cat and an what? Ion. What was the type of bond? Ionic. When you bond a metal to a nonmetal, look at all of your metals and look at their electronegativities. They are all very, very low, particularly in comparison to all of the nonmetals. Okay? That difference in electronegativity is enough that we can jump to the conclusion that ionic compounds are just metals and nonmetals. Ultimately, it's really coming back to the difference in electronegativity, and it's being defined as that. Okay? If we look at a covalent compound, what was a covalent compound? Nonmetal bound to nonmetal. Well, all of our electronegativities for our nonmetals have very high electronegativities. So what happens when I look at the difference in those electronegativities? Do I get a big number or a small number? Take a look at fluorine and fluorine. Two nonmetals, right? That's an eraser. What's the difference in electronegativity? 0. Is that a big number or a small number? Small number. If you have a small difference in electronegativity, what happens to your bond? It becomes covalent. Okay? So our definitions that we look at when we talk about Chapter 6 are really coming back to how do atoms share electrons? And that sharing effect is summarized in electronegativity. Okay? So we will keep coming back to this because it's something I keep hitting my organic students with. Okay? So if I hit you guys enough with it, eventually you won't have to worry about it if you ever see me again for organic. Should be fun. Okay? Questions? Don't look so depressed. That was good stuff. Jeez. Okay? One of the things that's going to come out of this is we run into ionic charges. So a term that you might see pop up is this term known as isoelectronic. Iso really just means same, and electronic is referring to electrons. So if we say isoelectronic, we're saying it has the same electrons. Okay, so let's take a look at a couple of these. Actually, let's not quite do that yet. You'll notice on this table we've got a whole bunch of elements kind of highlighted with their charges. Okay, these are their common charges. Some of them you need to memorize, some of them you do not. As a wild guess, probably should not memorize those. Okay, the ones I just crossed out. The two that are not on here, or the three that are not on here that you need to know: zinc plus 2, cadmium plus 2, and silver plus 1. Okay, you need to know all of these charges. Okay, we keep throwing stuff. You got to memorize this. You got to memorize this. You got to memorize this. Is there a shortcut?
Oh, there's a 1 above the silver and 2 is above the other ones.
Got a couple ways we can look at it. Column 1 has what charge? Oh, 1 and 1. Column 2? Plus 2 in column 2. Hey, that looks kind of nice. Column 3, or 13, plus 3. So the 3, we can subtract that 10 out of there and ignore it. Column 4, you notice we don't have anything written there. We'll come back to why we've got that in a second. Column 5, okay, it becomes negative 3. It's a little bit odd, but okay, we can sort of see some parallels. Column 16, negative 2, column 17, negative 1. So you can sort of pick up at least the positive charges off the column numbers. Okay? But there's another thing that we can evaluate. Okay, let's take a look at this isoelectronic. And I'm going to take a look at isoelectronic for that guy, for F minus. Which, if we know our nomenclature, F minus is called fluoride. Why is it not fluorine?
Because it's a vector charge.
The D is in reference to it being an ion. If it was fluorine, it's not an ion anymore. Okay, it would just be the element. Since we're looking at the ion, we're going to call it F minus, and we'll refer to it as fluoride. Electron configurations, because you guys are now awesome at this. Go ahead and recite them, starting on 3, 2, 1.
1s2.
There we go. We got a little excitement there. 1s2.
2s2. 2p6.
Why did you say 5? Okay.
2p4, 3, no, 2p5, just kidding.
So, fluorine. Okay, if we look at fluorine, it would be 2p5. This is fluoride. What does fluoride mean? I'm negatively charged. To be negatively charged, what do I have to do? I have to add another electron. What's the electron configuration for fluoride? 2p6. Also known as the electron configuration for neon. Yeah. It's kind of odd.
You should have to tell the difference between the two. You have them side by side.
When you're looking at the electron configuration, you wouldn't be able to tell the difference. Because the electron configuration is just the number of electrons. When you had the elements next to each other, you'd be able to tell because different protons. Okay. Let's take a look at this ion, N-3, also known as nitride. Why did you say "ide" and not "gin"? It's the ion. Okay, this goes back to our nomenclature rules. Okay, because it's an ion, it's nitride. Electron configuration. 1s, 2, 2s, 2, 2p.
Also known as sub.
Why is it 6? I look at nitrogen. Shouldn't it just have 3p orbitals or 3p electrons? It's -3, so I have to add another 3 electrons to it. So it becomes 2p6, also known as neon. Oh, that's interesting. Okay. What happened in those cases? We're just adding electrons in to make our atom look electronically similar to our noble gases. Why would we want to look like a noble gas?
Because of balance?
Because of symmetry. Our noble gases have that full electron shell completely filled out. There's no empty spots. Everything looks beautiful and happy. Okay? Which explains one of the reasons why our noble gases don't react. So when we're looking at our ions, what we're trying to do is get as close as we can to a noble gas. Okay? Trying to look all rich and hoity-toity. That's why we buy fancy cars. So we're trying to get to that, which hoity-toity or buy fancy cars. We're trying to look like the noble gases. Well, couldn't fluorine have looked like helium? What would fluorine have to do to look like helium? Helium's a noble gas. Why didn't fluorine go to look like helium? What does fluorine have to do to look like helium? We don't even worry about energy levels. It has to lose 7 electrons. Which is easier, losing 7 electrons or gaining 1? Gaining 1. Why does it not look like argon? It would have to gain, oh, that is 9. 9 electrons. Which is easier, gaining 1 or gaining 9? Gaining 1, unless it's a pizza, and then you gain lots. Okay, I got more out of that. That's good. Hey, we're waking up. Okay? So we're trying to do the easiest transition possible to get to the electron configuration of a noble gas. When we move to nitrogen, nitrogen's got the option of looking like neon or like helium. Okay, to look like helium, what would nitrogen have to do? Get rid of 5 electrons, or to look like neon, gain 3, which is easier. Gaining 3. Carbon. Do the exact same logic with carbon. Can look like helium or can look like neon. What does it have to do to look like helium? Lose 4. To look like neon? Gain 4, which is easier. Either, which is why you're not required to memorize it. Oh, that was supposed to be an eraser. Aluminum can look like neon, or it could look like argon. What does it have to do to look like neon? Lose 3 electrons. To look like argon? Gain 5, which is easier. Lose 3. Okay. Your charges are all about trying to look isoelectronic to your noble gas. Which of the noble gases is easiest for it to get to? That's where those common charges come from. Okay? So if you know how to derive that, then you can solve for all of those right away. Another option, let's just clear everything off of this. What's always included with your exam? Periodic table. You get your exam, the first thing you do, get your person's next to you's name on it, but then after that, flip to the periodic table and go +1, +2, +3, -3, -2, -1. Ta-da! You now have all that information written down. Any question I throw at you, it's already written. All you got to do is flip to your periodic table. There's the answer. Okay? But you say that's so easy, you'll never forget it. You're trapped in your head. Get out of your head. Bad place to be. Okay? Write it down. Okay? Questions? And I guess no, because you're all staring at me like I already knew this. Did you already all know this? No? Okay. Chapter 4 summary. So we got a quick summary here, and then I'll let you go before we start 12 next week. So chapter 4. In chapter 4, we subdivided it into 2 categories. The first part of chapter 4 was talking about famous dead people. Okay, so which said a little bit more politely, cool scientists. You got Dalton, Thomson, Millikan, Curie, and Rutherford. Okay? So what you need to do is make sure you review each of those scientists' names and what in particular they were famous for. Right? That's going to be important. One of the fun things that I can throw at you, you might very well see a question about, any guesses? Curie. What's even more fun about asking questions about Curie? She's not in the book. Yes, you show up to class, you knew what you were talking about. Okay? Subatomic particles, protons and neutrons. Okay? That's where we kind of went through with our cool scientists for the most part. We then move into the wave nature of light. This is continuous versus discrete. Those 2 terms are important terms. What's an example of continuous? A ramp, okay, is continuous. What's an example of discrete? Staircase. Bohr was a discrete gentleman, meaning what was his whole conclusions? We got another famous scientist here.
He had the staircase.
What about the staircase? It's the staircase example for energy levels for the negatively charged species, electrons. Okay? Bohr is famous for your atomic line spectra and the existence of electrons being in orbital homes. So you get your subatomic particles again with your electrons. You'll run into configurations, okay, which we just talked about, and your valence electrons. Your valence electrons are your highest energy form. Okay, chapter 5. Okay, again, split into 2 parts. We kind of went through the first part with general trends on the periodic table, and then we move into kind of more ionization energies and stuff. So you get Mendeleev periodic table predictions, trends with electron orbitals, chemical and physical properties, atomic radius, ionization energy, and ionic charges. The big one there, ionic charges. Okay, that is pretty massively important. Why is that massively important? It's how you do your nomenclature in chapter 6. Okay? Pretty sure that's it. Yeah. So where we'll pick up on Tuesday will be bonding, Lewis structures. We got some more kind of example stuff. I will get the bonding slides up over the weekend.